So, in this video, we're going to talk about the paper Determining the Sentiment of Opinions. This paper is published in 2004 on computational linguistics. This talk is organized in the following way. First, we will give a brief introduction about the problem that the paper tries to resolve. Then, we will introduce the workflow to determine the opinion and sentiment. Then, we will show the performance of the sentiment classifier in the results. By talking about the drawbacks of the paper, we will introduce related works to try to resolve the issues. Finally, we draw a brief conclusion. The main target of this paper is to find out people's opinions on a given topic. An opinion is defined as containing four elements: a topic, an opinion holder, a claim, and a sentiment. It can be expressed in the following form. The opinion holder believes a claim about the topic with a sentiment. For example, in a sentence, I think the US attack on Iraq is wrong. The opinion holder, I, shows a negative sentiment towards the topic US attack on Iraq and thus makes the claim. To achieve the target, there are four steps. First, we have to identify the opinion holder. Second, we delimit the opinion region. Then, we calculate the polarity of words. And finally, we combine the word polarities into a sentiment. To identify the holder, the paper used named entity recognition and only considered person and organization closest to the topic phrase. To find the region that contains the opinion, the authors investigated four regions, using the whole sentence, or words between the holder and topic, or the two extensions on the second region. In the part of word polarity calculation, seed words indicating positive or negative sentiments are grown using synonyms and antonyms from the word net. Given an unseen word, the polarity is calculated in two ways, both using the maximum a posteriori method. The difference lies in the calculation of the probability of the word's occurrence given a class. The first method uses a knife-based method, and the second simply calculates the portion of the word's synonyms in the corpus. Finally, polarities are combined in three ways, namely the signs, harmonic, and geometric averaging. The signs averaging is similar to the harmonic averaging, but uses the binary indicators instead of real values to represent the word's polarity. In the results section, we're going to see the performance of the polarity and sentiment classifier. This table shows a comparison between the performance of random selection and the first polarity classifier. From the table, we can see that the classifier outperformed the baseline. By adding more C words, performance can be dramatically improved. For the accuracy of sentiment classifier, the best performance is achieved with the second polarity classifier, the force window, and the signs averaging. So, to summarize, this paper proposed a method that finds the sentiment of an opinion holder on a given topic. These methods are very straightforward and intuitive, which can serve as baselines for future works. There are several drawbacks of the paper. The first is that the knife-based model is unable to handle context modifier. The larger sentiment spectrum is not investigated. And from the results, we can also see that the holder detection is very poor. The last drawback is that the paper assumes there is only one opinion per sentence, which is not always true in practice. Therefore, the paper does not provide useful enough results for practical applications.
Okay, so now let's talk about some of the drawbacks and how related work addresses them. In the 2004 paper, a naive-Bayes model is used. However, in the real world, the independence assumption of naive-Bayes does not really hold, and hence this model is unable to handle sentences in which contextual modifiers are present. For example, consider a sentence like, "I do not think that was a good movie." The sentiment of this should be negative, but the naive-Bayes model might assign a positive sentiment to the sentence if only the probability of positive sentiment given the word good is considered. This is because of the fact that not actually modifies the word good is not being considered. Hence, at the sentence level, we need a better way to reason about modifiers. Furthermore, the naive-Bayes model might not be expressive enough for handling large spectrum of sentiment or non-polar sentiment like sad, happy, angry, and so on. So, how do we address this? Firstly, single word models cannot capture the compositional meaning of phrases. The authors also point out that it is computationally expensive and also limiting to use n-grams with large n, as the amount of data required would grow exponentially. So, here we present two improvements which can handle this drawback. One is recursive neural networks, another one is convolutional neural networks. So let's talk about recursive neural networks. In usual RNNs or sequential models, words or characters are processed in sequence to obtain a representation at the end of the sentence, which can be used for the sentiment detection task. However, we present a paper that explicitly uses syntactic structure of a sentence as an input. The main idea of the paper is to use the syntax tree and figure out how to obtain intermediate representations at each node of the tree by combining words. So first, a syntax parse tree is obtained. Then words at the leaf nodes are combined at each intermediate ancestor node. To do this, vector and matrix representations are learned for every single word, for example, word A and word B. When combining two of these words, the vector representation of word A is multiplied with the matrix representation of B, and vice versa, and these are concatenated together. Then, a nonlinear projection function is applied. This is then the intermediate representation which takes the original word and modifies it, giving an adjective, for example. And you could keep doing this recursively bottom up the syntax tree. So mathematically, it would be expressed in this formula. These transformations give a final representation which is used for some downstream task. One example in our case is sentiment classification. So how does this model do? The authors try to estimate the true sentiment distribution of adjective-adjective pairs on a 1:10 scale and measure the KL divergence from the true distribution. Kullback-Leibler divergence is a measure of divergence of probability from some reference distribution. On the graphs here, we see that for different adjective-adjective pairs, the estimated probability of sentiment scores. Taking from the example of the word awesome, we can see how having different modifiers like not, which is negation, and unbelievable, which is superlation, the prediction distribution is changed. And the authors found that MVRNN did the best amongst the compared methods, which means that it is the most successful in modeling the distribution of sentiment given some modifying adjectives. Furthermore, the authors tried this model on a movie review dataset and found that it beat the state of the art by a significant margin. Therefore, we can say that this related work is able to address the context modifier drawback well, as it is able to capture how adjectives modify words, and on a downstream task of sentiment analysis performs much better.
So, another paper which handles the two drawbacks mentioned before is sentiment analysis using convolutional neural networks by Oyong et al. In this paper, the authors propose a framework called word-to-vec plus CNN. Firstly, they use the word-to-vec proposed by Google to compute vector representations of words, which will be the input for the CNN. That is, they created a matrix of 53 words by tokenizing each sentence. Each word is converted to a vector by using word-to-vec model. These vectors are taken as the input for the word-to-vec model. Let us first talk about what word-to-vec model is. Word2Vec is used to produce word embeddings. It is a shallow two-layer neural network that is trained to reconstruct linguistic context of words. It takes as its input a large corpus of text and produces a vector space, typically of several hundred dimensions, with each unique word in the corpus being assigned a corresponding vector in this space. The purpose of using word2vec is to gain the vector representation of words and reflect the distance of words. Similar words have higher cosine similarity. To illustrate this, if you look at the diagram, the words gorgeous and beautiful are very close to each other because they're very similar. This will lead to initializing the parameters at a good point for the CNN, which can effectively improve the performance of the nets in this problem. Secondly, let us see how to design a suitable CNN architecture for the sentiment analysis task. In the CNN model, 53 is the maximum number of words in a sentence for this dataset. Then, each word using word2vec is converted to a 300-dimensional vector, which is the input to the CNN model. This is passed through the first convolutional layer, in which multiple random filters are used. The filters help to consider contextual words in a window and use them as inputs rather than just a single word input like the existing paper. After this, there is a maximum pooling layer. In total, 3 convolutional layers and 3 pooling layers are used in this CNN. To train, a mini batch stochastic gradient descent is used. They also use parametric rectified linear unit, normalization, and dropout to improve the accuracy and generalizability of this model. The experimental results suggest that convolutional neural networks that are properly trained can beat shallow networks. They consider context within a sentence because of the convolutional filters acting as context windows. Let us have a look at the results. They tested the framework in a public data set, which is the corpus of movie reviews and includes 5 labels: negative, somewhat negative, neutral, somewhat positive, and positive. The proposed framework beats the existing sentiment models by achieving a test accuracy of 45.4% on Rotten Tomatoes movie reviews dataset, which is a better performance than some other neural networks like RNNs. Also, there is no need to label every word in the sentence. What is needed are the labels of the whole sentence. The larger datasets, along with the proposed deep CNN and its training strategies, give rise to better generalization of the trained model. Therefore, we can say that this related work is able to address the context modifier drawback well, as it is able to capture how adjectives modify words. Hence, it does a better performance on sentiment analysis task.
Okay, now let's talk about how to address the third drawback, which is a poor accuracy of opinion holder detection resulted by choosing the closest holder to the sentiment. Let's take a look at an example. A thinks B's criticism of T is wrong. So the original paper's approach would take the holder of sentiment wrong to be B instead of the correct answer A, simply because B is closer to wrong than A. So how should we address this? The authors of the original paper actually came up with this idea in one of the follow-up paper of using syntactic parse tree and maximum entropy model with ranking. Let's take a look in details of how it works. Now, here is the original sentence, and this entire tree structure is a syntactic parse tree generated for this sentence. From manual inspection, you can see that in this sentence, China's official Xinhua News Agency is the opinion holder of the opinion accusing. So right now, our goal becomes to find out the correct MP non-phrases, because you can see there are several of them, this MP and this MP. We need to find out the correct MP for these opinion, which is a verb, accusing. So how do we do it? Let's see. Basically, the users design a system of now we are giving a sentence and also an opinion expression. We first generate all the possible holder candidates given this sentence and opinion expressions. So now the candidates are labeled as C1 through C5. And then we do a parse of the entire sentence as I showed in the last slide. Now we have the syntactic parse tree. And then we extract features such as syntactic path information between each candidate, C1 through C5, and the expression E, and a distance, and maybe a distance between each candidate and E. And then we feed this information into the maximum entropy model. And the maximum entropy model would pick the most probable candidate of the opinion holder using this equation listed here. And then we simply we can just pick the best candidate as a holder. This is the results of using syntactic parse tree and maximum entropy model to detect the opinion holder. And these different columns are just results of using different combinations of features, because here you can see it only uses one feature, and here it uses all the features that the author discovered to feed to the model. And you can see that using all the features combined, it generates its accuracy actually doubles what that is for the baseline for the top one opinion holder identification. Okay, that's it for the improvement for automatic holder detection. Let's talk about the last drawback number 4, which is the original paper holds a false assumption that one sentence has only one opinion or aspect in order to simplify their algorithm. So basically, the original paper's method was able to capture different opinions in one sentence, but the authors just chose to detect the closest one. However, this assumption is inaccurate and incomplete if we want to extract useful information from texts for practical usages. Here is one famous counterexample. You can see that it is a typical customer review of a restaurant's several aspects, as its food, service, and ambience. Now the first sentence, the food was very good, but it took over half an hour to be seated, and the service was terrible. So this sentence expresses two sentiments on two different aspects, positive sentiment on food and negative sentiment on service. So as the third sentence. So the original paper would only catch one sentiment and totally miss other important aspects. So how do you address this? Basically, we need a more fine-grained level of examination of opinions in sentences. And we need to look at the problem from another perspective. And that's where aspect level sentiment analysis comes into place. Okay, now let's take a look at a specific implementation of such system. In this paper, the author implemented such system, and the structure is as follows. First, we would have a set of reviews, and we feed this as an input to a text extractor, which basically breaks reviews into a set of text fragments, including sentences, clauses, and phrases. And then we would feed this into a sentiment classifier, which basically classify each text fragments as positive, negative, or neutral. And then we would feed this into an aspect extractor, which basically, so here is the dynamic one and here is the static one. The difference is that for the static one, we need to input several aspects that we think are common in this specific domain. So it's domain specific and it improves the accuracy. And after this, after feeding the fragments with aspect extractor, we would get text fragments with both sentiments and aspects assigned. So this part. And then we will fit this into an aggregator and a summarizer to get a final summary. And let's take a look at one example results. This is done for a Greek restaurant's review, and you can see that we successfully divide the reviews into subtopics like food, service, and ambience. And under each subtopic, there are both positive reviews and negative reviews. Okay, let's take a look at the results of the performance. Here we can see that through different domains, restaurant and hotel, the precision for different subtopics are consistent and are really high. So it could be used for practical usages. Okay, that's it for aspect level sentiment analysis. Finally, the conclusions part. There are 4 drawbacks we concluded from the original paper. The first 2 are naive-based model incapable of handling context modifiers well, and the second can't handle larger sentiment spectrum. And these are resolved by related works of recursive neural networks, which explicitly make use of a syntactic structure, and convolutional neural networks, which learn filters over word-to-vec representations of sentences. The third drawback is a poor performance on automatic holder detection and is resolved by syntactic parse tree. The last drawback is the assumption that one sentence has only one opinion or aspect, and it is resolved by aspect level sentiment analysis. Okay, that's it for our presentation. Thank you for listening.